This is my fourth video lesson on Unit 12. In this lesson, we will determine the equilibrium constant. Go to page 16 in the class packet. Learning target. At the end of the lesson, I'll be able to determine and manipulate the equilibrium constant K. Homework will be number 4. The equilibrium constant expresses the relationship between the concentration of products and reactants at equilibrium. The symbol of the equilibrium constant is K or KEQ. If it's Kc, the products and reactants are in units of concentration. Here we have a chemical reaction. A and B are reactants, C and D are products. Here's the general equation of the equilibrium constant. It is products over reactants. The lowercase letters represent the coefficient in the chemical equation. Since the reactants and products are in brackets, it represents the concentration of the reactants and products. Keep in mind, if A, B, C, and D is a liquid or solid, they are always excluded from the equilibrium constant equation. Assume it is constant 1. The reason for this is because solid and liquid have constant concentration because they're incompressible. Now I'm going to show you how the equilibrium constant equation was derived from the rate law. So here is our chemical equation. A and B are reactants, C and D are products. The rate law of the forward reaction will only be based off A and B. The rate law of the reverse reaction will be based off C and D. So we know at equilibrium, forward rate is equal to reverse rate. Therefore, we can set the rate law equations equal to each other. If we put K on one side and the rest on the other side, we get our equilibrium constant equation. So K is a ratio between products and reactants. Now we're going to go over 3 simulations involving the equilibrium constant to help you visualize the relationships. All 3 simulations will involve the same reaction, the white circle, which is the reactant, and the black circle, which is the product. The forward and reverse reaction will be the same for all 3 simulations. For every period, for the forward reaction, about 1/3 of reactants become products. For the reverse reaction, about 1/4 of products become reactants. There will be some estimation here. Initially, before we start the reaction, we have 14 particles in the container. All of them are reactants. As we go through the simulations, you can color in your packet. Now we're going to start the reaction. In the first period, in the forward reaction, about 1/3 of reactants become products. 1/3 of 14 is about 4. So 4 reactants become products. Since there was no product particles to begin with, no reactants are formed from the reverse reaction. So we still have 14 particles, 10 of them are reactants, and 4 of them are products. This reaction can still continue. In the second period, in the forward reaction, about 1/3 of reactants become products. 1/3 of 10 is roughly 3, so 3 reactants become products. In the reverse reaction, about 1/4 of products become reactants. 1/4 of 4 is 1. About 1 product becomes 1 reactant. In total, we still have 14 particles. 8 of them are reactants and 6 of them are products. This reaction will keep going. In the next period, for the forward reaction, about 1/3 of reactants become products. 1/3 of 8 is roughly 3, so 3 reactants become products. In the reverse reaction, about 1/4 of products become reactants. 1/4 of 6 is roughly 1, so 1 product becomes 1 reactant. In total, we still have 14 particles. We have 6 reactants and 8 products. As the reaction continues in the next period, for the forward reaction, about 1/3 of reactants become products. 1/3 of 6 is 2, so 2 reactants become products. In the reverse reaction, about 1/4 of products become reactants. 1/4 of 8 is 2, so 2 products become 2 reactants. In total, we still have 14 particles, 6 reactants, and 8 products. Notice there was change, but there was no net change. we still have the same amount of reactants and products, even though the reaction is still occurring. If we do one more period, we're still going to get the same result. There is change, but there is no net change. The number of reactants and products are the same. We have reached equilibrium. The concentrations are constant, even though the reaction is still happening. Now let's determine the ratio of products versus reactants in each period. The ratio will be products over reactants. So for this one, it will be 4 over 10. For this one, it will be 6 over 8. And for the ratio at equilibrium, it will be 8 over 6. The ratio at equilibrium is the K constant. What do you notice about the numbers when the ratio is greater than or less than 1? If K is greater than 1, it means the equilibrium favors the products. There's a higher concentration of products than reactants at equilibrium. If K is less than 1, equilibrium favors the reactants. There's a higher concentration of reactants than products at equilibrium. And if K is equal to 1, there is about equal concentration of products and reactants at equilibrium. So here's a nice diagram to illustrate this. When K is less than 1, at equilibrium, the reaction mixture has more reactants than products. When K is greater than 1, at equilibrium, the reaction mixture has more products than reactants. And when K is equal to 1, at equilibrium, the amount of reactants and products are about the same. Now let's graph simulation 1 to see how the reactants and products change over time. Equilibrium is reached when the concentrations of reactants and products are constant, even though the reaction is still occurring. Now let's look at simulation number 2. We still have the same reaction with the same forward and reverse reaction. We still have 14 particles in the container, but this time we have a different amount of reactants and products. We have 4 reactants and 10 products. We are going to run the same reaction to see what happens. In the first period, for the 4 reaction, about 1/3 of reactants become products. 1/3 of 4 is roughly 1, so 1 reactant becomes 1 product. In the reverse reaction, about 1/4 of products become reactants. 1/4 of 10 is roughly 3, so 3 products become 3 reactants. In total, we still have 14 particles, but this time we have 6 reactants and 8 products. If we keep going, we will get the same amount of reactants and products. This is because we have reached equilibrium. The ratio of 8 products over 6 reactants is the same K constant as simulation 1. So it does not matter the starting amounts of reactants and products. If your forward reaction and reverse reaction are the same, then you will get the same ratio of reactants and products at equilibrium, and your K constant will be the same. So if you want to change the K constant for a reaction, you have to change the temperature. Changing the temperature would change the rate of the forward and reverse reaction. Adding a catalyst or changing the concentration and pressure will not change the K value. The next simulation will illustrate concentration change. In the third simulation, we have the same reaction with the same forward and reverse reaction. But this time, we'll be adding 7 product particles to a reaction at equilibrium. This is the same reaction from the previous simulation with the same K value. Since we added 7 products, our total is now 21 particles. We have 15 products and 6 reactants. The ratio is 15 over 6. This reaction is no longer at equilibrium. Now let's begin the reaction. In the first period, for the 4 reaction, about 1/3 of reactants become products. 1/3 of 6 is 2, so 2 reactants become products. In the reverse reaction, about 1/4 of products become reactants. 1/4 of 15 is about 4, so 4 products become 4 reactants. We still have 21 particles, but now we have 8 reactants and 13 products. The ratio will be 13/8. In the next period, for the 4 reaction, 1/3 of reactants become products. 1/3 of 8 is roughly 3, so 3 reactants become products. In the reverse reaction, about 1/4 of products become reactants. 1/4 of 13 is roughly 4, so 4 products become reactants. We still have 21 particles, 9 are reactants, and 12 are products. The ratio is 12/9. 12/9 is the same value as 8/6. Since we reached the same ratio as the reaction at equilibrium before we added the 7 products, we have reached equilibrium. If we continue this reaction with another period, we should get the same amount of reactants and products, which we do. This shows that changing the concentrations does not affect the equilibrium constant K. This simulation also demonstrates Le Chatelier's principles. When concentration changes, the system will shift back to equilibrium. Since we added 7 products to a reaction at equilibrium, the system responded by making more reactant, which happened. It went from 6 reactants to 9. In summary, K is the equilibrium constant that represents the ratio of products and reactants. If the symbol is Kc, that means the equilibrium constant is expressed in terms of concentration. If the symbol is Kp, that means the equilibrium constant is expressed in terms of partial pressure. Learning check number 1. What is the equilibrium law expression for the following? Pause the video, resume as completed. K is the equilibrium constant, which is products over reactants. Keep in mind, solid or liquid are always excluded from the equilibrium constant, so H2O liquid will not be in the equation. And since the coefficient of each substance is 1, the exponent or order for each substance is also 1. So the answer is choice 3. Learning check number 2. What is the equilibrium law expression for the following? Pause the video, resume as completed. Same as before, solid or liquid is always excluded from the equilibrium constant. So calcium carbonate and calcium oxide are excluded from the K constant because both of these are solid. So the answer is choice 4. For practice number 1, write the equilibrium constant K given the reaction. Try to do it yourself. Pause the video. Resume as completed. Here are the answers. For task 2, we are going to look at 3 ways to manipulate K. The first one is the reverse reaction. The K constant for the reverse reaction is K prime. K prime is equal to 1/K. For example, here we have a chemical reaction at equilibrium. The K constant is 0.212. Question 1. According to Kc, is the equilibrium favoring products or reactants? It is favoring N2O4, which is a reactant. For question 2, write the equilibrium expression of both forward and reverse reaction. The forward reaction is products over reactants, NO2 squared over N2O4. For the reverse reaction, everything is flipped, so K prime is equal to N2O4 over NO2 squared. Question 3. What is the Kc prime for the reverse reaction? It is 1/0.212, which is 4.72. Question 4. According to Kc prime, is the equilibrium favoring products or reactants? It is still favoring N2O4, which is the product of the reverse reaction. Learning check number 3. What is the K prime of the reverse reaction? Pause the video, resume as completed. K prime is equal to 1/K, so 1/1 times 10 to the 30th power is equal to 1 times 10 to the minus 30. So the answer is choice 2. The second manipulation is scaling the reaction. N is how much we're scaling it by. K prime is the K constant after we scale the reaction. Here we're given a reaction and the K constant, according to Kc, is the equilibrium favoring products or reactants. It is favoring products, ICl. If the reaction is scaled by 4, what is K prime for the scale reaction? It will be the K's constant raised to the 4th power. According to K prime, is the equilibrium favoring products or reactants? It is still favoring products. Learning check number 4. The following reaction will be scaled by 3. What is the K prime of the scale reaction? Pause the video, resume completed. K prime will be K raised to the 3rd power, so the answer is choice 1. The last manipulation of K is combining 2 or more K constant. To do that, you'll be multiplying the K constant to combine them. Let's look at an example. Let's say your reaction has 2 steps, step 1 and step 2. K1 represents the equilibrium constant of the first step. K2 represents the equilibrium constant of the second step. So K1 is equal to AC over A times C. K2 is equal to AC2 over AC times C. Let's say you want to figure out the K constant of the overall reaction. All you need to do is multiply K1 and K2. Or you can write out the overall reaction and figure out the K constant from that. The K constant of the overall reaction should be AC2 over A times C squared. This K constant should be the same as K1 times K2. Notice they are the same. Learning check number 5. What is the K prime of the combined reactions 1 and 2? Pause the video, resume completed. If we multiply K1 and K2, we get choice 4, 2 times 10 to the 3rd power. Try to do practice number 2 by yourself. Complete questions 1 to 9. Pause the video, resume completed. Here are the answers. In task 3, we'll be solving for K given the equilibrium concentration. Let's look at example 1. Calculate the value of the equilibrium constant K and K prime for and reverse if 0.1908 moles of CO2, 0.0908 moles of H2, 0.0092 moles of CO, and 0.0092 moles of H2O vapor were present in a 2-liter reaction vessel at equilibrium. Here's the chemical equation. The first step is to write the equilibrium constant K equation, which is products over reactants. Since in the question we're given moles and liters, we have to convert to concentration. Concentration in terms of molarity is moles over liters. Once we get the concentration, we can plug it into the K constant equation. K is equal to 4.9 times 10 to the minus 3. To get the K of the reverse reaction, we just flip it. K of the reverse reaction should be 1 over K of the forward reaction. Learning check number 6. Consider the following reaction. What is the numerical value of the equilibrium constant K at this temperature? Pause the video, resume completed. The first step is to write the equilibrium constant equation. That will be Cl2 times NO squared over NOCl squared. This is based off the chemical equation. The next step is to plug in the concentrations at equilibrium, and we get 0.27. So the answer is choice 1. Learning check number 7. An equilibrium is established in the gas phase. The equilibrium concentration of both NO2 gas and N2O4 gas are 0.1 molar at a constant temperature. What is the value of the equilibrium constant K at this temperature. Pause the video, resume as completed. The first step is to write the equilibrium constant equation. That'll be N2O4 over NO2 squared. The next step is to plug in the concentrations at equilibrium into the equation. 0.1 over 0.1 squared gives us 10. So the answer is choice 4. For practice number 3, calculate the equilibrium constant K for the forward and reverse reaction. Complete questions 1 to 14 by yourself. Pause the video. Resume as completed. Here are the answers. This concludes the video lesson. Remember to do the homework.